Let us review the use of matrices, the mathematics of matrices, in preparation for our lecture on state space representation. Let's look at first the sizes of matrices, how to carry out addition within matrices and subtraction, how do you do matrix multiplication, what is the transpose for a matrix, and how do you get a matrix inverse. So a matrix, it's in general, it's a block of numbers in 2 dimensions. It's called a matrix. So this is a matrix, is a 2 by 2 matrix, and the size of the matrix is called in terms of, it's named in terms of rows by columns. So you have rows and columns. So you have a row matrix, for example, matrix, in fact, it's called a vector. The vector A, this would be a row vector. 3, 4, 7, 12. So this would be a row vector. It has one row, the special case of a matrix which is called a vector, which has only one row, which has only one row, and then this would be the multiple columns. A column vector, this is an example of a column vector, is a 2 by 1 matrix or column vector. So this one would be, in this case, it would be a 1 by 4 matrix. If I cancel that, this becomes a 1 by 3 matrix. Yeah. An example of a 2 by 3 matrix would be when I have 2 rows, so I'll have row here, and then 3 columns. So I have 2 rows, 1, 2, I have 3 columns, 1, 2, 3 columns. So it's a 2 by 3 matrix. And then I can have an example of a 2 by 2 matrix. So that could be an example of a 2 by 2 matrix. And because the number of rows and columns are equal, so there are 2 rows, 1, 2, and there are 2 columns, 1, 2. Because the number of columns and rows are equal, it's called a square matrix. Another example of a square matrix would be a 3 by 3 matrix. So this could be an example. This is an example of a 3 by 3 matrix, which is also a square matrix because it has 3 rows and 3 columns. Now, matrices like ordinary numbers, we can carry out the addition and subtraction of matrices. However, the most important thing here is to remember is that they have to be the same size. So in this case, if you have a 2 by 2 plus a 2 by 1 here, 2 by 2, let's say 2 by 2 plus. So here you have a 2 by 1, and then you're trying to add it to a 2 by 2. Because now you're trying to add different sizes, this size is different from that size, this cannot happen. You can't add those matrices. Similarly, if you have a 3 by 1 minus a 2 by 1, this you can't compute. Cannot compute this because the sizes are different. So this is 3 by 1, this is a 2 by 1. It's different. However, you can have 2 3 by 1s, and then you can subtract that. And the way you subtract it is you go corresponding element to corresponding element. So this would be equal to 3 minus 1, 1 minus 2, 4 minus 1, which means the result here is 2, negative 1, 4. So that is the result of the subtraction here. You can have another type of a square matrix here, 2 by 2, you have 1, 2, add it to another one. 5, 1, 2, sorry, 2. You can add these twos because you're adding each element to each element, to corresponding element. So you add this to that, and the answer you write it here, and so on and so forth. So here this would be, the result would be 6. You add the corresponding elements, 2 plus 1, you add 2 plus 1, you have 3, and then you add 3 plus 2, you have 5, you have 4 plus 2, you have 6. So that would be the result of the addition. So another important aspect of matrix manipulation is multiplication. So with multiplication, the sizes must match. They don't have to be equal, they have to match. What does that mean? This means the sizes of the matrices must have a matching pattern. So for example, if you have two matrices, a matrix of size k by n can be multiplied with a matrix of size n by r, because the two n's here, they correspond, they are equal, and the result will have a size k by r. Let me give you an example. So an example would be when you have a 2 by 1, you want to multiply that by a 1 by 3. So if you have that 2 by 1 multiplied by a 1 by 3 matrices, this will be okay. And the resulting size of the size of the result will be 2 by 3. Another example is, if say you want to add a 3, you want to multiply a 3 by 3, and you want to multiply it by 1 by 3. Now in this case, this won't work, because this one is not equal to 3. So you have to, you can only multiply matching sizes. So here, if you want to multiply a 1 by 2 times a 2 by 1, you can multiply. You can have a 1 by 2, 2 by 1. This can be multiplied because the 2's match, and the result is going to be 1 by 1, which means it's just going to be a single digit. Here as well, if you have a 2 by 2 and you want to multiply it by 2 by 1, because the two adjacent numbers are the same, this will work, and the result will be a 2 by 1. And in this case here, you want to multiply a 2 by 3 with a 2 by 3. The sizes are equal, but they don't match, because these two adjacent numbers don't match. So this won't work. It won't work. So let's make an example now of how this should work. So when you do your multiplication, you do your multiplication row by column. So in this case here, we have a 2 by 2, and we want to multiply it by 2 by 2. So because these two numbers here adjacent to each other, they match, this can be multiplied, and the result is going to be 2 by 2. So you have the first matrix here and the second matrix here. Now the way you multiply this is we use row by column. We multiply a row by a column. So the first thing that we will observe is that the answer we know is going to be 2 by 2. So it's going to have a result here, a result here, a result here, and a result there. It's going to be a 2 by 2. And the way we multiply, I said we should do it as row by column. So what does that mean? This means that if you are looking for this result here, we are going to multiply the first row. So the first matrix will always give you rows, and the first column. So you multiply the rows of the first matrix times times the row of the second matrix, and that should give you this result. If on the other hand you wanted this result here, then what you're going to do is, because this is on the second row, you're going to take the second row of the first matrix, and because it's on the first column, you're going to take times the first column of the first matrix, and then this should be your answer. If on the other hand you are looking for an answer to this number here, this digit here, because it's on the second row, second column, you're going to take the second row and then you multiply it by the second column, and the combination of these should give you the answer here. So let's make then our first example. So we want to multiply, we want to get this result V. Because of that, it's on the first row of the first column, so the first row is involved and the first column is involved. So the way we do it is you multiply 0 times 1, and then you add that to 2 times 3, and that gives you 6, and that 6 you need to write here. That will be your answer here, which is this one, right? And then you move on to the second one. So you move on to the next bit that you want to multiply. This is on the first row and the second column. So for that, to achieve that, you multiply 0 by 4. You add that, so it's 0 by 4. You add that to 2 times 2. And that answer, you have to write it here. And the answer of 0 by 4 is 0 plus 4, which is equal to 4. So the 4 will have to come here. And this is why we have a 4 here. Now we want to consider this part. This is the second row of the first column. So we'll have 5 times 1 plus 3 times 3. And the answer will be 14, which is here. And then for the final bit, we'll have the last, sorry, remember the first matrix will always give you rows, not the columns. So we'll have the second column and the second row, and the result should give you this, where the two correspond. And then we have 5 times 4 plus 3 times 2, which is equal to 26. So that's how you get your result. Another important operation that you can do to a matrix that you will see in many of the applications is what's called a transpose, so transposition. So a transpose simply says you write the resulting matrix, you convert the rows to columns. Your rows becomes your columns. And the way the transpose is shown is by a superscript T or a superscript dash. So if I have, for example, a vector, a column C, and I have that dash, this means the transpose of C. If I have another matrix P and I have a dash, that means the transpose of P. Or I could have P and then superscript T. It also, so sometimes you see this representation, sometimes you see that representation. It means the same thing. It means the same thing. So now, as an example, if you have a vector here, this is a what? This is a column vector. It's a column vector. In fact, it's a matrix of size 2 by 1. So there's 2 rows, row 1, row 2, and 1 column. Now, it therefore means that the transpose of V, you're converting all the vectors into columns. So you're converting all the rows into columns. So how many rows do we have? 1, 2 rows. Now that row, the first row, we convert it into the first column. The second row, we convert it to the second column. This way. So we simply twist it. So this would be the transpose of the vector. And then if you have a row vector like this, if you transpose it, you're going to have a column vector. If, say, for example, here you have a matrix A with the following elements, If you transpose that, it means this row will become a vector. So you're going to take this row, and then this row will be the first vector. The second row will then become the second column. So that's how you translate, that's how you transpose in that case. So if you have an example, if A is 1735, then the transpose will take that into that, and then this into that. So which means your A transpose is going to be 1375. If on the other hand A is, for example, 1, 2, 5, 6, 7, 9, then your A transpose is going to be of a different shape. So because here you have a 2 by 3, so this is going to be 2 by 3. It means the transpose is going to be 3 by 2, because your rows becomes your columns. And then the first row will become the first column, and then the second row will become the second column. So that's how you do your transpose. Now, before we talk about the inverses, which is another important aspect that you must know of matrices, I need to remind you again of a determinant or determinants of matrices. A determinant of a matrix is a scalar function of a matrix, and sometimes it's written like an absolute value of the matrix. So if you have a matrix A, this representation simply means the determinant. For the purpose of determinants, we are only going to be calculating determinants of 1 by 1, which is 1 by 1, which we know what it means actually, or 2 by 2. So we're going to be calculating those two determinants. Now, for a 2 by 2 matrix, the determinant, if say for example you have your matrix A with A11, A12, A21, A22, the determinant is defined as this subtraction. It's going to be the leading diagonal here, A1 times A22, minus the lagging diagonal A21 times A12. So let's get an example here. So let's say we have an A here, and we wanted to do a determinant. The determinant will be the leading diagonals elements times each other, 4 times 3, minus the lagging diagonals, which is 1 and 2. So here you're going to have 12 minus 2, which is equal to 10. So 10 becomes the determinant of that matrix. Another example here, we have a determinant of A, in this case the determinant of A, we are going to have 2 times 3 minus 2 times 4. So this is going to be 6 minus 8, and then the answer is going to be negative 2. So which means determinants can be negative as well. So the determinant is negative 2. And if the determinant of the number is not equal to 0, then we say that matrix is invertible. That's a term that's used. So we say it's invertible, which means we can have an inverse for that matrix. We'll later learn or be reminded, in fact, what an inverse is. So in this case, this is an example of a non-invertible matrix. We will have 2 times 0 as the determinant, minus 0 times 1. So this is going to be 0 minus 0, and the answer is 0. Because the answer is 0, the determinant is 0, we say this matrix is non-invertible. Another good example of a non-invertible matrix is this one, where we will, to calculate the determinant, we'll take the leading diagonal, 1 times 2, 2 minus 2 times 1, which is 2, and then the answer is 0. So this is another example of a non-invertible matrix. In fact, in systems which we are controlling, we don't like this non-invertible systems. They clearly spell trouble in control problems if your system has such a matrix. Now, if we want to look at an inverse of a matrix, first let's look at what an inverse actually means. So an inverse is a number to the power -1, which simply means that number divided by, so 1 divided by that number. So in fact, we notice that a number times its determinant is actually equal to 1. So there is something, there is an equivalent value for a matrix, there's equivalence or equivalent representation of a matrix, which is called an inverse of a matrix. So if you have a matrix A to the power -1 is called an inverse of a matrix. In fact, what's interesting is that it's an inverse because when we have that matrix, if you multiply it by its own inverse, it should give you what we call an identity matrix. An identity matrix is a matrix that has ones on its leading diagonal and 0 for the rest of them. So this is an example of a 2 by 2 inverse, a 2 by 2 identity matrix. A 3 by 3 identity matrix will look like this: 1 0 0 0 1 0 0 0 1. So this would be a 3 by 1 identity, sorry, a 3 by 3 identity matrix. So the way we calculate the inverse is if we have a matrix A to the power -1, such a matrix can be written, so we can write this actually, in fact, that the matrix A11, A12, A21, A22 to the power -1. How do we calculate the inverse? The way we calculate the inverse is we do it in 2 steps. First, we find the determinant, and then what we do is we say that the inverse of that A would be equal to 1 over the determinant times a new matrix which has been reorganized. So the new matrix will be reorganized in such a way that the diagonal elements here of the leading diagonal, they swap. The A11 moves to the spot, exchanges spots with A22, and then the lagging diagonal elements are just simply made negative. So that means we have now created an inverse of the matrix A. So the steps are: you calculate the determinant, and then you swap the main axis and negate the leading. You swap the main axis of the leading diagonal, and then you negate the rest of the other elements. Let's have an example of how to find an inverse. So let's say you have a matrix here, A with 10, 4, 6, 2. So we say the first thing is to find the inverse of this matrix. So the first thing is to find the determinant. So determinant will be the leading diagonal elements. We multiply them together. So we have that times that. 10 times 2 minus 4 times 6. 10 times 2 is 20 minus 4 times 6 is 24. And then it means the determinant is -4. Now therefore the inverse is going to be 1 over the determinant, and then we swap 10 with 2, we swap this, so 2 comes in place of 10, and we negate the rest. 4 becomes negative and 6 becomes negative. And then in fact we can take this 1/4 and multiply it throughout. So we find that this becomes our A inverse. So in fact, because we know how to verify the inverse, we know that if you multiply a matrix by its own inverse, we should get an identity matrix. So we can do that calculation here. So for instance here, for this first element, we need to make the first row times the first column. So it's 10 times -1/2 plus 4 times 1.5. So this becomes 10 times half. This becomes -5 plus 4. 4 times 1.5, this is 6. And then if you add the 2, they give you 1. And then you have on the second element 10 times 1. plus 4 times minus 2.5, and this gives you 0, and so on and so forth. So you can verify this. Take your time to verify that. And then I think as a recap, then we can say, in order for you to calculate an inverse of a matrix A is the first step, find a determinant, and then multiply by 1 over determinant, rearrange the leading diagonal members, negate the lagging diagonal members. So having reviewed setting a reminder on matrix manipulation, I think then we are ready to learn the third alternative way of representing systems, which is called the state space representation, as I will commonly call it. I think the reference book that you have will call it state variable representation. So when you come across video tutorials on the internet or any other book, you might find they use these terms interchangeably, the state space or state variable representation. So let's go and learn state variable representation.